interesting. And thank you also, Alex, for the invitation. My privilege to be here today. So just before I launch into the talk, I just wanted to talk a little bit about Hariba Myra, if you've not heard of it before. But it's a company, an advanced engineering consultancy company based out in the Midlands with a proving ground and all sorts of very exciting things happening around connected autonomous vehicles, hence why I work in the field, specifically looking to secure it. Now, before I begin talking about cybersecurity, I just wanted to speak very quickly on some of the terms and definitions that we're going to use here. So for those who are or have been involved in cybersecurity before, one of the sort of explosions in terms of the connectivity that we're seeing and also the increase in sort of autonomous smart decision-making in machines and other areas such as industrial control systems and factories is this term cyber-physical systems. And the reason it's called cyber-physical systems, it's got computational elements, so the cyber part that we're really used to, but it's also got physical elements that are interconnected, they're networked to form a cohesive cyber-physical system. And the difference between this and security per se, an IT network, is that there is an actual physical response in anything that's happening. So if we take a look at a robot, a car, anything to do with IoT, factories, because they have an actual physical response to a cyber element, we have to take into account something that we've never really had to take into account before in cybersecurity, and that's safety. And I'll be talking about security and safety and how they interact with each other at some point, because obviously, it's an important element, and we don't want to forget about it. But security is the area where it also ensures not just safety, but a whole host of other things as well. I also wanted to introduce how I see cybersecurity, especially for people who've not been involved in the field so much before. And the first is, I know it's a little bit small, it's my favorite picture of cybersecurity, but that's a barrier across the road, and it's a perfect product, good barrier. Obviously, it doesn't quite cover all the vulnerabilities that there might be, and here we can see the security exploits, what people have done to get around the security that we've put in place. But obviously that's not it. We're actually seeing, an almost infinite vulnerability space that would need more and more and more protection as time goes on if we were to feasibly keep everybody else out. And that's the point about cybersecurity. It's about feasibly keeping someone else from doing whatever it is they want to do. So if we take this analogy, if we expand the barrier, we may not be able to make it perfect, and we may not be able to cover everything, but at some point, people who want to get into that car park are going to give up and go somewhere else, and that's what we want. So that's generally cybersecurity, but in the connected autonomous vehicle field, in the future mobility field, I wanted to talk a little bit first about what we know. So what do we know about connected autonomous vehicles and the security behind it and the implications thereof? The first is we know somewhere artificial intelligence is going to be an enabler, a key enabler of autonomy. It enables it to learn decisions, learn from its environment, and so forth. So we know somewhere on the vehicle at some point, in an autonomous vehicle, we're going to see some kind of artificial intelligence. But not just on the vehicle, probably see it off-board as well and communicating with it off-board. There'll probably be some mixture of the two. This is what we know for sure. Obviously, there's a lot of work going on right now in terms of how much, what proportion, what kinds, and how often, and so forth, looking at best data sets and so forth. But generally, we know there'll be some kind of off-board computation happening in collaboration with what's on board. Seeing a whole array of sensor technologies, and this is key as well because obviously if the autonomous vehicle is not able to learn or communicate or take in information from its environment, then not going to be able to do much with it to make it autonomous. So we want to make sure that there's a whole array of sensors and that they're at different levels. Some are based on light, some are based on sound, some are based on radio frequencies, so covers all our bases. Connectivity, key. So if we want the vehicle to be able to predict, to forecast, to see things that are further away than just its immediate environment, we want to make sure that it's connected, and it'll be what I call hyper-connectivity. It'll be connections, not just from car to car or car to infrastructure, but connections within the vehicle, connections to the cloud, connections to whatever else is going on around it as far as we can make it, because that's the only way it would be able to predict and forecast accurately enough. Underlying it all is data. So lots of talk right now of data security and how we can secure data on and off the car and how we get things securely on and off the car. And data obviously is the basis of how we use these technologies. And overlaying all of that is what I call public trust and acceptance, or public readiness, or what the public can or should see for them to be able to trust that the car is secure and safe. So this is what we know about CAV enablers, and I'll come back to it a bit later in terms of security implications, just to kind of bring CAV to you. Now, in terms of security, it's always been a balancing act, as I'm sure you know, for those who have been involved in any kind of risk analysis. The first in the autonomous vehicle field, and actually in most embedded systems field, is this issue of constrained systems. Now, with normal computers and high-performance computing or even just your phones, a lot of these systems have a lot of power in them, and some of our best defenses are actually based on that power, based on the fact that we can protect against such power. So let me give you cryptography. One of our best defenses, not feasible on many embedded systems because they're very computationally heavy. And on a vehicle, for example, of today, the most powerful chip you might see is in the infotainment system, which would be no more powerful than a phone. But that's just the one part of it, not the whole part of it. There are as many as dozens of microcontrollers inside a vehicle, and not all of them are as powerful as the infotainment system. So, that holds true of cars. It also holds true of even more constrained systems like medical devices. Especially the implantable ones, they have to be small and therefore are very, very constrained in both their space and computational powers. Unfortunately, the signals that we tend to want to protect most in the car, for example, tend to be the most time-critical ones. So if you think of decryption as computationally expensive, it will cause latency to the point where it slows down your brake signal, say, which is obviously not very great. So there's a balancing act with constrained systems. The other thing that we're seeing in autonomous vehicles and most other sort of really big embedded systems type systems is long life cycles, and there's two aspects to this really. The first life cycle is the design life cycle. On average, currently, it takes a manufacturer about 7 years to design a car and put it out there. 7 years. In computing terms and cybersecurity terms, that's quite a long time. On top of that, once it's been designed, it's expected to be on the road for an average of 12 to 15 years. So from the time it's first conceived to the time it comes off the road, we're talking a good 20, 25 years. That is an era almost in terms of computing. And we can see that not just in cars, but also in ships. So cars, 12 to 15 years. Ships, we're talking more like 40, 50 years. Infrastructure systems like what's out on the roads, factories that you've built, you don't expect them to have to change every 2 or 3 years. You want them to stay for a long time. But it comes balancing act-wise with the problems that come with legacy systems, legacy protocols. I don't know if you've seen, but lately, in the last couple of weeks or so, there was an advert out for NASA for a program of Fortran. And the reason for that, of course, is some of the probes that have left that are traveling far away from our solar system was made in the 60s and 70s, and then they used Fortran, and unfortunately, they can't find the skills now. So it's one of those areas that we have to consider when we're looking at designing security and maintaining security for any long-lived system. The supply chain and dealerships, lots of buzzwords and things out there around Industry 4.0 and smart manufacturing and all the rest of it. And it's actually really important because security tends to be more of a holistic thing. You want to look at a system of systems, and it also tends to be only as good as your weakest link. So in terms of your supply chain, not really your supply mesh, because I'll come on to that a bit later, but in terms of your supply chain, if you can poison something, one thing in the chain, then whatever ends up in your final product is going to make the whole product weak. That's supply chain downstream, but we've got also supply chains upstream. So looking at, specifically for vehicles or autonomous vehicles, when we look at dealerships, things that sell things, they also have the same problems in that they bear some of the reputational liability. You know, they're like your frontline IT system. If your vehicle was hacked, the first place you would go, or if your vehicle was broken down or anything, first place you would go is probably to a dealership and say, fix it for me. So they've got to be aware of all these issues as well. They also have all the traditional IT cybersecurity things to deal with, and some of them are acting as data centers for some of the information that's now coming off the car through debug ports or for diagnostic purposes or for maintenance purposes. So if we're talking about monitoring and maintaining cars, dealerships have got to be in on it as well. Now, it becomes a little more difficult because they're not always belonging to the manufacturer. Some of them franchises, some of them subsidiaries, and of course, in different countries, dealerships work differently. So lots of balancing acts required there if we're talking cybersecurity for the ecosystem. Updates is another one. This is actually tied to the life cycle part of it. But if you were to update a vehicle over the air, there's a lot of both technical and logistical issues around updates. When should you do it? How should you do it? There have been trials in Michigan, for example, to look at public key infrastructure and how you revoke certificates. Where and how would you do it? What if there was no signal? How would malicious activity, if it was a malicious update, propagate through a network? Very similar to network security, except that in terms of vehicles, there are also ad hoc networks that kind of form and change topology and shape and size on an ad hoc basis. So there's extra challenges to deal with on top of that. And last but not least is legislation. So we do know legislation for cybersecurity is coming. Great. The only thing is there are several layers of legislation. Some are automotive specific, so we've seen some of them in terms of autonomous vehicle bills coming out, Spy Car Act in the US, where they talk about cyber dashboards and security requirements. So those are nice and clear. They apply to vehicles. But then there's a whole host of IoT cybersecurity legislation coming out. Now, some IoT don't explicitly reference connected cars as IoT. Would it apply to them then? Some don't reference it either way, so they're not explicit about it. Some are just implicit. And some of them just say, well, only consumer devices, but I don't know, is a car a consumer device? Possibly. There's also a sort of layer of legislation that was never meant to apply to the car in the first place, but because of the changing nature of vehicles, autonomous vehicles, and the ecosystem around it, they now do. So an example of this is financial transaction systems. We're already seeing them being deployed on cars. Now, for those of you who've been involved in the financial industry, there's a set of regulations called PCI DSS that apply to point-of-sale systems. These were never really meant for cars. They're meant for sort of cashier systems, but they do apply because now we have point-of-sale systems, both in cars and in the infrastructure around it. Another example is GDPR and privacy. Again, never really meant for vehicles or the automotive industry. It was meant to be for anyone who was a data controller. But now the car is gathering data, gathering quite personal data, and I'll give some examples of that later. So these are some of the things we know, or at least some of the known unknowns, some of the problems that we're working towards at Mara and at other places as well, and I'm sure here at BT also. But there are also some kind of problems that are, at the moment, intractable or made up of many different parts and very, very complex areas. And this mostly has to do with future mobility. A lot of it is because we don't have solid things to look at right now. We don't have a vanity test. We don't have, fleets of autonomous vehicles out there running day by day to take a look at. It's very much in simulation, in theory, and so forth. And a lot of it is limited because cybersecurity data tends to be sensitive. So knowledge sharing is another challenge that we're having to balance with. So I wanted to introduce, in terms of future mobility, this Internet of concept. I know a lot of you probably won't need introduction into the Internet of Things, but I wanted to posit that actually what we're seeing really with connected autonomous vehicles is the Internet of Vehicles, which is a superset of an Internet of Things. That's because there are many things on the car, and I'll get to that in a bit. And it's just a subset of what I've called Internet of Everything, which is things. One of the pillars of Internet of Everything is things, but also data, process, and people. And I'll be running through this why it's an Internet of Everything as the talk goes on. So in terms of things, speaking about the cars of today, we already know that in terms of cybersecurity and security attacks and legacy systems, that CAN is susceptible. It is a legacy protocol. It's not protected in any way. It is obfuscated, so that does add to the difficulty. But this obscurity is not really a whole defense. It's only part of defense. So there have been many, many demonstrated attacks on CAN, including plugging into the OBD2 port to program new keys so that you can steal the car. We've seen them tap into the CAN bus to inject signals for all sorts of mischievous purposes, demonstration-wise. So CAN is one of the areas that's well understood. The OBD2 port, or the onboard diagnostics port, is a mandatory port required for you to sell cars. Every car in the world pretty much will have one, otherwise the car can't be sold. And it was originally meant for diagnostics and for sort of open access to independent garages and for sort of environmental data as well. But over time, manufacturers began to see that it was an easy port, seeing as it has to be there anyway, that they would make it multi-use. The OBD2 port has been implicated in a lot of real-world, what I call real-world attacks, because they've been used a lot in terms of theft of cars, at least in the early days of car theft through electronic means. The immobilizer is another one, another early target. So the immobilizer does things like won't enable the fuel injection system or has an electronic steering lock until you have an RFID pair between key and whatever is on this immobilizer. So again, early days would be to try and override it, to steal the car mostly, or to replace it altogether using electronic purposes. So another sort of early vector. Keys are the most recent vectors in car theft. So lots of reports on relay key attacks, which is basically the effect is the amplification of the distance between the key and the car so that the car thinks that the key is next to it. It targets what's called a passive key entry system, where you have the key somewhere on you, but you don't need to press anything to open the car doors or start the engine. Keys of today also hold a lot of data. They hold things like number of standing starts, some information about driving style, how many times it's been started, how many times there's been a sudden stop. Some of them hold GPS data. So the reason for this is insurance fraud. They want to make sure that you're not committing insurance fraud, and they will check data on the key to correlate. But that also has privacy implications. CD player, this was an attack demonstrated in 2010 by some researchers in the US. And this, I keep bringing this up because even though it was demonstrated in 2010, it's a great example of how even correct functionality can be misused, and that goes back to my favorite picture earlier about cybersecurity. So the CD player in this case, these researchers put some code on a CD, they encoded it as music, they placed it into the CD player, and the CD player played the music. Did exactly what it was supposed to do. Unfortunately, in playing the music, it also executed the code and caused the ECU to reflash. And from there, they were then able to pivot into other things. But this is a classic case of not just correct functionality being misused, but also excessive functionality, and excessive functionality that's also probably not correct, but unspecified, really. So took advantage of that. Lots of Wi-Fi. Wi-Fi is nice low-hanging fruit. Doing quite a lot of work in it at the moment in terms of how it can be used, how it can be protected beyond the normal. We're also seeing cellular connections coming out of the car. And in fact, since April 2018, almost every car sold in the EU has to have an eCall system, which is to say a telematic system, which is to say it needs some kind of cellular connectivity. And this is, of course, the one of the techniques or the basis for the infamous Cheah in 2014-ish. So those are the things we know about today, things that have been demonstrated in the real world and or actually used for criminal purposes, ON sensors, so things around ultrasonic sensors, radar, and so forth. But I wanted to bring in more things around what we're seeing so far being deployed in some vehicles, not all vehicles, kind of precursors to the full connected autonomous vehicle we might see in the future. And one of them is predictive management systems, whether it's for battery management or for efficiency or fuel efficiency, power efficiency, range efficiency, that sort of thing. That's what these predictive management systems are for. Could be a good vector. I mean, if we talk battery management systems, for example, our batteries are very, very safety critical. They also manage things like temperature. And when the battery gets too hot, well, there's a risk of fire, so it's not great. If they're based around machine learning, then all the traditional security implications of machine learning, like poisoning the data set, would apply. If they're taking the examples from that environment, we must make sure that the environment also remains within a certain range, otherwise it could be used to take advantage again of these predictive systems. I bring up telemedicine, and what I mean is in-cabin occupant monitoring. Lots of talk on how to monitor the health of the driver or the car. So are they stressed? Are they angry? Are they about to fall sick or faint? Are they too tired? Are they drunk? Lots and lots of areas around this. And of course, then we have to consider not just the privacy aspects of this, but also the cybersecurity of the data, of the biometric data that's being created. Wireless charging, so this is more towards the connection with infrastructure, not just wireless charging, but charging in itself. I mean, we're talking financial transaction systems being there, and we know when you start putting money in the equation, then the criminals start looking at it with interest. But not just the financial aspects, we want to make sure, of course, that there is a privacy aspect to it, that you can't track how often the car uses something or where they stop to use the car, because you could track their journeys then. But also on top of that, because it is a cyber-physical system, that's the safety aspect of it. Can we protect it against malicious inducement of faults? Because malicious inducement of faults means that there's a safety problem. So we've got lots of peripheral devices happening. So smartphones being used as car keys or as remote starters or being used to park your car. We're seeing, talk around linking wearables to the vehicle and the whole in-cabin monitoring thing. So I bring this one up because what it does is expand our boundaries over what it used to be. So before, when we talked about a vehicle, we could talk about the subcomponent, and we could talk about the hardware and how we stop that from being tampered with. We could talk about the car itself. But now we've added smartphones, and from smartphones, it's all the other connections to those smartphones, and from those connections, to infrastructure with the charging. So suddenly our boundaries are getting bigger and bigger, and for security purposes and for security work, that makes it much, much more complex. Personal assistance, as an example of some of the artificial intelligence that we're seeing already in our vehicles. So certain manufacturers in the US have already introduced Alexa. So there's been demonstrated attacks on personal assistance, one of which was being able to send covert instructions to Alexa through ultrasound, so an out-of-band channel attack. And these just kind of demonstrate that people do think outside the box, and it goes back to that picture of going outside those barriers. Telematics I've mentioned, and what I've called offboard computation, and this again is another example of the boundaries expanding. So by offboard computation, we're talking lots of networking principles, we're talking the cloud, and suddenly we're talking the whole world. It gets very confusing, and it gets very, very complex. In terms of what we know and what we don't know, this is one of those areas where we can kind of see the trends based on other domains, other sectors, other technologies, and other research in the autonomous vehicle. And this is the reason why I've said that it's a superset of IoT, but a subset of everything. Because once it gets to the area where it's connected to the cloud, has all kinds of very complex algorithms, and brings in so many different technologies from so many different sectors for so many different purposes, that's where it gets, that's where we need some kind of, some help, really. External monitoring, I think I've mentioned anyway. Oh, and different networking protocols. So not only is the vehicle itself opening up, we're starting to see within the vehicle different networking protocols, different technologies, and they inherently bring in some of the weaknesses of that particular protocol. So there's plenty for the Internet protocol, there's plenty for the Ethernet protocol, and one of the things we might want to consider is how we port in the defenses that we've built, all these decades into the normal sort of networking protocols in the vehicle, taking into account its constrained systems, its long life cycles, and so forth. So that's more things. So that's things. But we want to be considering the other pillar as well. And so here's an example of the data aspect of it. Now, I've mentioned before that machine intelligence or computational intelligence would be a key enabler. And in this case here, we can see some of the major areas that machine learning and artificial intelligence is used for. And I put them in the context of autonomous vehicles, and then I further divided them into the context of defense or offense. So on the defense side, we're talking, understanding attacks and attackers, making sure that path planning is safe. But what I wanted to bring up here is that whatever we use as a defense, the criminals can also use as an offense, using exactly the same techniques, exactly the same data sets, and they just have a different aim in mind. And what one of the predictions is that we're going to be talking about an arms race. Now remember, they haven't really yet turned their eye to the autonomous vehicle industry, not in earnest, but they are paying attention. And I'll talk about this more in the people aspect of it, but they are paying attention, and this is one of those areas they're paying attention to. So some of the areas of research that we're involved in MIRA is looking at security for AI and AI for security. So how do you verify something that's constantly changing? How do you do it with high confidence? And how do you make sure that it stays that way if it's constantly changing? The slides will be made available, so you don't have to read it all now. But yeah, it's an interesting concept. The other part of it is the data jigsaw. So this goes back to what we know and what we don't know. So we actually know some of the attack targets. We've seen it in terms of the interfaces they go for, especially with low-hanging fruit like Wi-Fi. We've seen it in terms of, because they're aiming for financial gain, like in theft of cars. We know some of the entry points into a car, and we're able to even rank them relatively to each other. How easy is it? How expensive is it? How many people can do it? And so forth. We know some of the methods they're using. Some of it's similar to, at an abstract level, it's all the same, as you would find traditional cybersecurity. At a more granular level, we know some of it's using some of the same methods, but using different tools and techniques. Which brings me to patterns. So we know in terms, if we abstract the autonomous vehicle away into being an autonomous system or a connected autonomous system instead, we're then aware of the patterns of attack that could happen around it, some of them anyway. We know some of the actors, or we know some of the potential actors based on data we have from law enforcement, from the information sharing that's going on around the world, and we know based on some of the demonstrations that we see researchers do, and we know some of the motivations. There's only really one at the moment, it's money, as it always is, but of course there are others. What we don't know, we haven't really seen any of these more advanced attacks in the wild. I mean, they must be happening, but a story around this, an anecdote I have around this is a grey hat looking at probing their own vehicle. They bought it new, on warranty. They probed it and they bricked it. Because it was on warranty, they thought they'd go back to the dealership and say, the car's broken. And the dealership went, I'm so sorry, let me replace that for you. They went and probed it again and bricked it again, and they went back to the dealership and said, it's broken again. I mean, come on. And the third time they did that, I mean, they didn't go back a third time because they were told then it'd be a quality assurance issue and would be investigated more deeply. We actually have no idea if some of these things have actually happened. And actually, that brings me to forensic system design. We don't plan for such things to happen, so we don't plan to have anything in place to record such things, or to, we may have planned some prevention or some tampering, tamper-proof or sabotage-proof hardware, perhaps even some software, but we don't plan to be able to record such things and learn from them, not in the vehicle and not outside the vehicle, not currently. that also brings me to at scale. So because we don't plan to record these things, record these events so that we can do, temporal analysis or any kind of analysis over a certain amount of time or over a certain scale, we actually don't know what the effects might be at scale. We can simulate some of it. We can use some theories behind it. But, how many cars would it take to gridlock a city? Probably the data for it is missing because we don't know of any attacks in the wild, and the data for it is probably also missing because we don't have anything forensic to record it. Coming back to my point about the car opening up, we actually don't know where the boundaries are anymore. We don't know where we should place the boundaries. There's been some talk around some of the trends we've seen recently in cybersecurity with regards to decentralization and deperimeterization, the removal of the perimeter and removal of the central controlling factor. And we can see that happening in vehicles in the automotive industry and in connected autonomous vehicles as well. Trying to see where these boundaries are is quite difficult. And part of it is because we don't have any metrics. We have absolutely, at the moment, no way of measuring it objectively, how all this works. How do we measure resilience to something? How do we measure how effective something is? How do we measure how good an attacker has to be? If we take into account all the risk analyses methodologies we have now, they're quite qualitative. They say, well, this is a novice level thing and this is an expert level thing, but my expert might be different to your expert. There are some standards which look at saying, the highest level takes multiple experts, but do you mean multiple experts of different disciplines, or do you mean multiple experts of the same, or both? Who knows? So because of all these very, very fuzzy sort of definitions, and because of the differences in sectors and use cases, we haven't seen one metric that says, right, this is X unit secure, and this is X unit able to recover, and it takes a person X unit ability to break through. So big area of research at the moment, actually. And that means we don't have any trust, of course. From a technical point of view, but also from a public consumer's point of view, policymaker, legislator's point of view, there's no trust. And that could be an issue, especially if you're manufacturing what to sell or you want to offer a service around this. Bias is another one. It's another balancing factor in terms of data. Of course, we want to be biased. We want to be biased towards safety, actually, and we want to be biased towards efficiency. But that bias we need to then balance against the security implications thereof. An example here is I could make a car 100%, an autonomous vehicle, 100% biased towards safety, in which case it might never move. It's probably 100% safe in a garage and never moving. So we want to make sure these balancing factors include security as well. The garbage in, garbage out thing comes from the point around not enough data, missing data pieces, nothing that's recording the data that we need. At the moment, we're just scoping out the kind of data we might need and the dimensions of those data we might need to answer these questions. But just being aware of this particular principle. And also that correlation is not causation. Now, I don't really have an example from the autonomous vehicle field, but I can give you one from the medical field. So a lot of work being done at the moment in terms of medical AI for diagnoses, so computer vision to look at X-rays and things like that and all sorts of scans to diagnose for certain things. And one of those was to predict the prognosis of pneumonia sufferers if they had asthma to begin with. And the AI predicted that people with asthma had a better prognosis for pneumonia than people who didn't. Now, that sounds back to front, and that's because the AI didn't take into account the context around it, which was that human doctors realized that asthma sufferers had worse prognoses, so they were treating it more aggressively, and that part of the data hadn't been put into it, so it turns it around. So that was the data aspect, but of course, data and things won't be connected without a process. And here, we can talk about processes for security assurance. This is one of the things that we're pretty good at. We've got lots of experience from all sorts of sectors, all sorts of fields in security assurance. So we're talking, standards and best practice and testing, analysis. It gives you confidence, but it doesn't give you a guarantee. And that's one of those, things that we just have to live with as cybersecurity experts sometimes, that at some point there is enough confidence. My work in high confidence methods actually looks to see if we can make that even better, actually give mathematical proofs and representations for this confidence. But we have a lot of experience in it as a community and as practitioners. Governance is also something that's coming along quite well. So we've got, lots of different legislation coming out, lots of monitoring in place, especially if it wasn't, not in such new areas maybe, but we can bring across some of those best practice over. Compliance, response, incident management, and deterrence, we've got loads of experience with that. One of the areas that's still sometimes a bit squishy is conflict resolution. And that's because a lot of the time this depends on the actual use cases and potential abuse cases in that particular sector or area. So in autonomous vehicles, one of the biggest conflicts actually, even though they do overlap, is security and safety. Let me give you an example of one of those. For an emergency response, which is a very safety critical thing, we want to make sure that time is of the essence, right? So we take the human out. Generally, the whole point of autonomous vehicles is we take the human out. For security purposes, we want the human to be in the loop. That's why we have multi-factor authentication. We have someone in the loop saying, hang on a minute, this doesn't make sense. Or hang on a minute, this doesn't, we need to make sure that this is really the person or really the thing that it should be doing, which slows things down. So that's a bit of a conflict, a balancing act there. Security and privacy is also a balancing act. So I'm sure you all know we can make sure that we enhance and we protect privacy with security techniques, but actually if we monitor everything all the time and make sure that there are forensic system designs in place and all the rest of it, we do possibly might compromise on privacy. Security and usability, age-old balancing act. Of course, in an autonomous vehicle, it takes on a slightly different flavor because almost every other form of transport, whether it has an autonomous mode or not, usually has a trained operator at the helm. That's so not the case with what we envision as a fully autonomous vehicle. At level 5 autonomy, we're basically talking taxi and passengers, a machine taxi. And then there's lots of stuff around usability that kind of comes into play. Would we need a remote operator or would the remote operator be human? Would it be AI? Do we need to tell them? How much information do we need to give them? Do they need continued help, only some help, a little bit? What do we tell the occupants to do in an emergency? Do we tell them to get out? In what language and how, at what level? They might just be children. It might be elderly. It might be someone who has absolutely no experience with technology. So lots of factors there in terms of security, because any gap in those requirements or any excessive or missing requirements in that area would mean that someone who is malicious would be able to take advantage of it. And the last one is security and cost. So obviously another age-old balancing act. But we need to be able to say that security in an autonomous vehicle is an investment to get manufacturers and those who might be a little bit reluctant because of the cost of it to really give it a go. So that's the process aspect of it. And then we come to people. Now, for those involved in the cybersecurity world, starting to see this platform criminality come to play. It's almost like a black mirror, a dark mirror, if you will, of what we have today. So we have software as a service, mobility as a service, platform as a service, and they have crimeware as a service. They've got software writers just the same as us. They've got engineers just the same as us. In fact, the really key attacks, the equipment that was used to steal these cars, having examined a lot of them, most of the time it was not the actual person doing the stealing who made them. They wouldn't have had the skill. It was actually engineers working for the organization that made them to give to the people who are on the front lines actually stealing the cars. So we're seeing a lot of these new ways of doing things being mirrored in a criminal world. And why not? It makes a lot of money. This figure here, for example, 1.5 trillion. It was an estimated number in 2018, and this is the number for the revenue that the cybercrime economy generates. This is at least 1.5 trillion. The researcher who looked into this was only able to find information on very high-profile things like ransomware and data breaches. 1.5 trillion. That obviously overlaps with the damage that cybercrime causes, which is 6 trillion. So if 6 trillion was the GDP figure, it would be second only to China. And 1.5 trillion would be about 13th. Still a lot of money. So you can see there's a lot of money in the thing before we even look at the opportunity that future mobility gives us. And with that sort of number, I'm pretty sure the criminals will come in, and they're coming soon. So definitely need to consider that angle. The second is around privacy. Now, I'm not talking privacy technically or even privacy according to legislation, but I'm talking about sort of what the public would say or do if they knew cars or other machines could do what they do. So, this one, for example, suing Uber because a wife found out about an affair, applying for a patent to detect drunk passengers, driver fingerprinting, DNA data breach, divorce. These are not illegal things. They're not wrong, per se, but they are private. And especially, when we consider things like biometric data in a vehicle, and one of the issues that I have with that personally is that I can change my password if there's a data breach. It's much harder to change your DNA, probably, I say much harder, impossible. So in these cases, just really want to be aware of the privacy aspects of it, because they impact on the ecosystem as a whole. And the last area of people that I wanted to talk about is skills. So, sure, everyone's aware, cybersecurity, much needed occupation. And it wasn't until I looked into the figures, actually, about cybersecurity in general. And the reason I go with cybersecurity in general is because future mobility, as you've seen, encompasses so many factors and so many sectors. There's a 6 million demand globally, currently, more or less, for cybersecurity people. There's 3.5 million vacancies. We're missing more than half of the people that we need. And this is with 0% unemployment. Pretty much everybody who studies cybersecurity has a job. So, one of those areas there, more training required. And I wanted to bring up a little plug here for the Mara Technology Institute, so automotive cybersecurity being one of those things. Just a very quick one, don't worry. And the last bit here is the ecosystem. I just wanted to bring together that ecosystem. I've talked about supply chain upstream and downstream. It's not so much a chain anymore, it's more like a mesh, a big mesh. Because there are certain providers who are both service providers, component providers, platform providers. Where do they fit in the chain? They're more like a mesh. And this little graphic here just gives you an idea of how big such an ecosystem is. It's probably even bigger than that now, snapshot. So to summarize, the Internet of Everything and future mobility and cybersecurity. In terms of things, at this point in time, it's still largely unregulated, and that means, a whole bunch of these things are proliferating and converging and conflicting. We're integrating things with other things into cars and other modes of transport that have profound effects on our lives, and we need to make sure that they're well protected. And also make sure that we take into account that some of these systems will end up being legacy systems. I haven't mentioned this so much, but quantum technologies are on the horizon. At this point in time, there's no public key infrastructure for the automotive industry, and with quantum computing making it realistic that you'd need quantum safe cryptography in the next couple of generations, maybe, of cars, we need to be thinking about that now. Data, so still missing many, many pieces, but we have to keep garbage in mind, we have to keep correlations, not causation in mind, and actually, even though we're looking at metrics and looking at how to predict and measure something, actually, it may not be measurable by a single piece, and we might have to take that into account as well, but actually, we don't know until we have more of the data pieces, the missing data jigsaw pieces. Process need to cover many, many aspects, and also the sort of conflict resolution aspect of it. And it's important to remember that cybersecurity is an overall system property, so we don't want to be just concentrating on the vehicle. We want to be concentrating on all the connections that it has as well, even though that does mess with our boundaries. And in terms of people, multiple angles of people again, you know, who can take advantage of it, who would benefit from attacking a vehicle, and who do we need to help with that? So this is just a slide based around our Vehicle Resilience Technology Center, and if you're interested, just, you know, MAR Vehicle Resilience. And it's a service that we offer, and actually we're working quite closely with BT right now on a project called ResiCAF, which looks at some of these problems here. But also, if you're interested in further collaboration or otherwise, then let me know. These are my contact details. So thank you very much.
Thank you very much, Madeline. Fascinating talk, and also slightly concerning. I think that resonates with how much work I think still needs to be done. Are you welcome to open to questions?
Yeah, absolutely.
Yeah, any questions in the room, first of all? Madeline,
yeah. Thank you for the interesting talk. So I work in Conveco, so my question is around connectivity. Mm-hmm. You mentioned the Internet of Everything, and I carry this to mention 6G as a word.
Yeah.
So one of the use cases of 6G is connected robotics and autonomous systems, I guess. So that's what we are anticipating to be what's driving the connectivity. So have you started looking at that, or do you have any comment or observation on what that is going to look like, cybersecurity-wise?
Yes, I think that's going to need a lot of automation, is what I think. The trend seems to be to connect everything up, and when you have so many pieces to take into account, and especially with the skills shortage and so forth, with 6G, with the speed and the amount of things you can transfer back and forth from so many systems, we're going to need to concentrate our efforts on automation. Automation of security knowledge, of security practices, security testing, and I think that's the only way we're going to be able to keep up with it. Already, I mean, you can see this going back to the black mirror, or dark mirror, if you will, that the criminals are starting to automate their attacks. So why shouldn't we automate our defenses and use this hyper-connectivity to get those defenses where they need to be as quickly as possible?
Cool. Any more questions in the room? No? Sarah, are there any coming through? I had a question, just sort of if you could give us a feel around how the automotive companies are evolving, because as you sort of, the picture you painted was essentially what we will have in the near future, if we don't already, is automotive companies are essentially supplying and having to maintain a distributed enormous data center on wheels, right?
Yep.
So are they evolving in terms of upskilling their own sort of IT network, you know, how much they provide, or is it really all about partnerships, and is there an opportunity for obviously BT to have a play in that space?
I think very much partnerships will play a key part in this, especially with companies and organizations who've already had so much experience in dealing with some of the issues that we see here. I think they are shifting to accommodate some of the processes of these businesses, so we're probably going to see a center ground where, you know, I talk about long life cycles, but if we take safety into account, it does take longer. We need to make sure it's safe, and that's one of the impacts that safety has in terms of the design of something. But then also seeing a shift towards more flexibility, more agile methods, which then complement nicely with companies who've looked at data and the software and networking aspects before, but not the embedded systems or cyber-physical systems aspects before. So I think we're going to see a middle ground and probably something out of that, especially when something interdisciplinary happens, probably find a lot of new processes that takes both into account taking place. So seeing a move towards that, definitely.
Anything coming through online, sir? No, nothing at all. Okay, if there are no further questions, I think we can thank Madeline one more time. And yeah, thank you.
Thank you.